Hello, good morning, and welcome to the first webinar organized by two Eurocluster projects, EuroBoosTEX at textile level and xBUILD EU, with the participation of the textile, construction, and advanced manufacturing. Before starting the webinar, I would like to explain briefly the calls that will be open on 3rd April by both projects, and that may be of the interest for you. The first one, EuroBoosTEX. EuroBoosTEX is going to launch the first call on 3rd April to fund new-to-firm products or services, and we will have a budget of 150,000 euros. We expected 10 SMEs, and the financial support for each participant will be of 15,000 euros. With these projects, the different participants can include as eligible cost, the direct staff cost, other direct cost, subcontracting, and also indirect cost. To see more and being updated with more information, you can join your LinkedIn profile. You can see here. The projects will start on 1st September. And the second project, xBUILD EU, is going to launch 3 different calls on 3rd April. The first one at individual level, the Innovate Grant, with an available budget for 8 projects. The maximum amount for each project will be of 20,000 euros. And the goal is to launch to market an innovative product or develop a new service. Then we have also the Green and Digital Grant. For this, we can grant till 4 projects. These projects will receive a grant of 50,000 euros. And the goal is to facilitate new solutions in the frame of digital and also circular environment. And the last one is the Global Grant for internationalization, and in this case, the aim is to promote the internationalization of the companies discovering a new target market as the Middle East. All of them will have a duration of 4 months, and all of them will be launched on 3rd April. You can follow in our LinkedIn profile to be an update for more news. And for all of you that can be interested to participate in these calls, we are going to prepare an info day on 12th April at 11 Central European Time to explain and to answer all the questions that can arise for your participation and these calls. And now we are going to start with our first webinar. It will be around green technologies in textiles, chemical, mechanical, and biorecycling. And for this, we have Aide Gaona. She is the Director of Research and Development Projects related to the chemical recycling of textiles waste, polyester and cotton, and the development of fibers from biopolymers, mainly PLA and PHAs. And today we are also waiting for Javier Pascual, but he's not available at this moment. So I think we can start with this webinar. It will be focused on these topics: the current state of the textile industry, the recycling technologies, and also an update about the biopolymers and the global market trends and recent developments. With this, we would like to give the floor to Aide and also to welcome to participate in this webinar. Aide, the floor is yours. Can you share your screen?
I'm going to share my screen. So, okay, good morning, everyone. Again, thank you for joining us in this webinar. As Julia commented previously, my name is Aide Gaona. I work as a R&D project manager in EuroBoosTEX, and I'm going to do a brief presentation about green technologies for the textile sector. And also, I will briefly analyze the current state of biopolymers and the recent development made for EuroBoosTEX in this field. Well, the presentation will be divided into three sections. Firstly, the current state of textile industry regarding the global market and the environmental aspect will be commented. Secondly, a summary of recycling technologies and the most relevant aspects will be done. And thirdly, an overview of the biopolymer current state, as well as the recent development made in EuroBoosTEX in this field will be described. As commented in this first section, I will give you a few actual figures about the market and environmental aspect of the textile industry. So, as you may know, textile industry is one of the world's most important sector, and it constitutes a significant part of the global economy. In the last 20 years, the global fiber production has doubled and is expected to grow exponentially in the coming years. The current system for producing, distributing, and using clothing operates in an almost completely linear way, and this, linked to the fast fashion concept, have driven to a substantial amount of clothes disposed in landfills and incineration. In fact, it is estimated that more than half of the fast fashion produced is disposed of in under a year. More specifically, in 2021, the global textile production increased again to a record of 113 million tons, and it is expected to increase up to 149 million tons in 2013 if business continues as usual. Within the textile industry, polyester and cotton have dominated the sector with a market share of 54% and 22%. Respectively. So both fibers together represent around 80% of global market. The rest of the market is covered by man-made cellulosic fibers such as viscose, lyocell, or modal, or other synthetic fibers such as polyamide, propylene, acrylic, or elastane, but with very lower market share. Regarding the recycled fiber global market, according to the bibliography, in 2021, the overall uptake of recycled fibers compared to the total fiber production was just around 8.5, being 7.9 recycled polyester from plastic bottles and only around 0.6 all other recycled fibers. Among the recycled fibers, polyester had the highest recycled fiber percentage with around 50%. However, around 99% of the recycled polyester was PET bottle based. So in overall terms, the reported figures are devastating since less than 1% of textile waste was recycling into new clothing in 2021. Therefore, increasing the uptake of recycled fibers is a key strategy with vast potential to reduce emission in order to mitigate climate change, prevent biodiversity loss, and reduce water consumption. How is possible these environmental problems with textile? And that's why textile production requires a considerable amount of energy and water. And in fact, it was estimated that in 2020, fashion industry used 93 billion cubic meters of water, generating around 1,700 million tons of CO2 emissions. And also it was responsible for producing 92 million tons of textile waste, as well as releasing nearly 1 million tons of plastic microfibers into the ocean. Therefore, circularity principles need to be implemented throughout all stages of the value chain, from designing to production, that's it, all the way to the consumer. As a result of the new European legislation included in the European Green Deal, European countries are obliged to collect textiles separately by 2025, achieving a collecting ratio of 55%. So currently, on average, 38 of the textiles placed on the market are collected separately when the consumer no longer wants them. This is based on the average of the European countries, with a lower average of 12 for Spain and a higher one of 60 for Germany. So the difference is really higher. These rates are reached through collection via containers, usually complemented with indoor collection system at first or second-hand retail stores. So based on this policy landscape, some of the key policy levers to foster something and recycling to enable circularity across Europe have been identified. For example, to introduce a mandatory eco-design requirements to enable the perspective on fiber-to-fiber recyclability, then it will be very interesting to include minimum recycling content targets. Also, aligning rules for sorting criteria for reuse and recycling could help to harmonize the sorting industry standards and requirements to prepare textile for reuse and recycling. And finally, consider digital labeling and product passport to enhance material traceability efforts for the end of the textile value chain. Well, wait. Well, second section is addressed to recycling technologies, highlighting technical aspects, challenges, and limitations. So, the textile waste hierarchy pyramid is a set of 5 priorities for the efficient use of resources. Waste prevention is at the top of the pyramid and is the preferred option. Subsequent steps, including reduce, reuse, recycling, energy recovery, and finally safe disposal, which sits at the bottom of the pyramid. More specifically, recycling technologies are classified in primary to quaternary processes. Firstly, primary recycling refers to remake or reuse. This is the most popular process due to its simplicity and low cost. This recycling requires that the chemical and physical constitution of the materials be not changed in the operation. Then secondary recycling includes mechanical reprocessing of used materials into products while downgrading properties. Tertiary recycling, or also called chemical recycling, considers those processes where the polymers are converted to monomers or depolymerized to low molecular weight oligomers through chemical reactions. And finally, quaternary recycling implies the recovery of the energy content by incineration. As commented, primary recycling is based on remake and reuse. This recycling requires that the chemical and physical constitution of the waste materials be not changed in the operation. For example, for consumer textiles are made into new material with low technical requirements.
No sé si son vosotros, si en general.
product lose some of its property like strength, stability, color, and so on. Then secondary recycling is a well-mature technology which is industrially implemented for many years, mainly for pre-consumer textile. That's its textile waste produced during the fiber processing. This recycling approach can be separated in two: mechanical recycling and also thermomechanical recycling, which depend on the textile composition. Well, more specifically, mechanical recycling can be used for any type of fibers. This approach relies on tearing and carding to separate the fibers, which can be spun into new yarns or used to make non-woven fabrics. The benefit of this approach is that the structural integrity of the fiber is preserved, but its length is reduced, which affects the quality of the recycled fiber. For this reason, recycled and virgin fibers are usually mixed to make a stronger textile and more competitive product. This approach is cheap and has a low footprint, and it's by far the most used method, especially for cellulose fibers like cotton and wool. Unfortunately, this approach is very limited because batches are susceptible to contamination and quality drops with every cycling, leading to a downcycling process. As commented, secondary recycling also includes thermomechanical recycling. For this approach, only thermoplastic polymers can be used because they are remelted and reprocessed into recycling materials. This process is represented by a physical method in which the thermoplastic wastes, such as PET, polyamide, or polyolefins, are formed by shredding and washing into granulates or flakes for manufacturing and melting to make a new virgin pellet by extrusion processes. After the plastic is sorted, cleaned, and dried, then is directly processed into end products, and the quantity of waste plastic is dramatically reduced. And the main cons of these methods refers to the heterogeneity of the solid waste and deterioration of the product's properties in each cycle, which occur due to the low molecular weight of the recycling resins. It happens because the chain season reactions caused by the heat fusion and mechanical stress, as well as the presence of water, colorants, and trace or impurities. This is why most clothes are recycling mechanically lose around 75% of their value. So they are used for application with lower technical requirements, such as injection species for automotive sector, for example. Well, the third recycling method is chemical recycling. These processes transform waste textile materials using specific chemical processes which enable the production of fibers featuring properties that are equivalent to those of the initial fibers. These technologies are based on chemicals, and they should rely on their reuse in order to environmental sustainable from the point of view of the process itself. Chemical recycling of textiles offer numerous benefits to the environment. It helps to reduce the amount of waste and the amount of water, energy, and resources needed in the production process. Well, I was with the solvent purification process within the chemical recycling, and I was commented that the basis of these technologies is used to the solubility principle to selectively separate polymers from other contaminants. In this process, the fabric is shred and dissolved in a solvent where the polymer has a high solubility, but the contaminants have low solubility. In this way, the pollutants remain solid and can be separated from the liquid fraction to purify the polymer. Once the purification process is complete, the polymer is extracted from the solution by resolidifying to allow the recovery in a process mainly by precipitation. The cons of this method rely on the mixture of different solvents and their toxicity, and also that we have to know the exact composition of the input in order to use the proper solvent. And maybe this it could be a really barrier for the implementation at industrial scale. In fact, recycling through solvent purification is yet to reach commercial scale. For example, companies such as Born Again Technologies has developed a technology which is able to process and separate and recover PET and cotton from blends through this process, but the problem is when you recover the material, they should be further processed through melting processes and like in mechanical recycling. So this process has a limited number of recycling cycles. So to my view, it's not a completely recycling, it's not a completely chemical recycling, because the definition of chemical recycling should be a process which you can obtain a virgin resin or a resin with similar properties to the virgin. So in this case, you recover the fiber or the resin in the same degradation level that it was in the waste. So this technology has this kind of barriers, and as commented, the effectiveness depends of the waste input and the degradation level of the fabric. I was commenting about the chemical recycling and the three methods of the chemical recycling. And the second recycling method is catalytic depolymerization. During this process, chemicals are used to degrade the complex textile polymer to create smaller polymer molecules or monomers. Thus, the monomers are recovered from the reaction mixture and purified through distillation, precipitation, or crystallization to separate them from contaminants and recover the pure monomer. Accordingly, monomer output can be used to produce new virgin resins, aiming at producing textile products of equal quality to virgin equivalent. This approach has been widely used for polyester and polyamide. In the case of polyester, the strategy of its depolymerization involves the cleavage of the functional ester groups by reagents such as glycol, known as glycolysis, water, called hydrolysis, methanol, methanolysis, ammonia, and amines. Among these approaches, glycolysis, hydrolysis, and methanolysis are all pathways that have demonstrated success at pilot plant level or larger, being glycolysis the most advanced in terms of demonstrating commercial viability on a larger scale. In this approach, bibliography describes that the effectiveness of the polymerization depends on employing specific solvents, process conditions, and catalysts. Solvents can improve the mixing of the polymer with the chemical inputs, but the quantities required on an industrial scale, as well as their toxicity, can be barriers to viability when scaling up the process from laboratory to plant. Temperatures and pressures are also often used to reduce the time frame over which the reaction occurs, but however, their use must consider the associated energy input, which has an impact from in the policies pathway is the most developed approach, which has reached commercial demonstration in comparison to methanolysis and hydrolysis. Well, accordingly, this map shows the company that are using chemical recycling of polyester at commercial scale. In this sense, Ionica, Cure, Carbios, or Green are examples of European companies that are building up commercial plants for polyester depolymerization. In the case of polyamide, the company Econil can be highlighted as an example of chemical depolymerization approach at commercial scale, which use a hydrolysis process to obtain recycled polyamide resin with similar properties to the raw material. Well, as previously described, the third chemical recycling method is thermal depolymerization. This process is also known as thermal cracking, and through this approach, polymer chains are broken down using heat treatment. Within this method, there are two main approaches according to the use of oxygen as a reagent within the process. For example, pyrolysis uses high temperatures in absence of oxygen, while gasification employs low volumes of oxygen to aid the degradation process. In the case of gasification, it converts plastic inputs into a gaseous mixture of carbon dioxide, carbon monoxide, hydrogen, methane, water, and other like hydrocarbons, collectively known as syngas, by heating at high temperatures between 700 and 1,500 degrees. On the other hand, pyrolysis typically takes place at moderate to high temperatures between 300 and 900, and atmospheric pressure to afford a liquid fraction, which is known as pyrolytic oil, as well as char and gaseous bioproducts. The advantages of this method relies on the many different kinds of raw materials that can be used in these processes, while the cons are the high temperature required and the energy consumption. While thermal depolymerization has received significant attention, it has so far failed to achieve commercial viability on an industrial scale due to the trade-off between energy inputs and quality of outputs. In fact, despite this is a mature approach in other fields, for plastics, packaging, or something like that. In the case of textile sector, there are not current examples of successful plant of textile at commercial level. Well, the next section 3, as previously commented, is focused on the biopolymers field. and namely in the global market trends and the recent developments in the textile industry. So, well, first of all, the most important question is what is a biopolymer? Well, a biopolymer is defined as a polymer produced from natural sources. Secondly, we wonder, but what benefits they do provide? The most important benefit is firstly that they are produced from renewable sources. The second one is that they reduce the carbon footprint since they produce fewer greenhouse gases over their lifespan. And finally, the third benefit is their higher possibility of biodegradability and compostability. Regarding their classification, biopolymers can be divided according to their origin and biodegradability. So based on their origin, we can differentiate three families. The first one is natural biopolymers such as collagen, cellulose, chitin, or starch. The second one is synthetic biopolymers like PLA, PCl, and PBS. And finally, the third group is microbial biopolymers, such as PHA family, where the most highlight polymer is PHB. Regarding their biodegradability and according to European bioplastics, a plastic material is defined as a bioplastic if it's bio-based, biodegradable, or present feature of both properties. So based on this definition, they can be classified into three groups. The first group is composed of bio-based or partly bio-based, but non-biodegradable, such as PE, propylene, polyester, or polyamide, which are partly bio-based, and or totally new biopolymers such as polyethylene furanate, also known as PEF. The second group includes bio-based and biodegradable plastics such as PLA, PHA, PBS, or starch. And the last group includes plastics that are based on fossil resources, but they are biodegradable, such as PBAT or PCl. So within this scenario, it might be highlighted that the most suitable polymers are bio-based and biodegradable. That's its PLA, PHA, PBS, and starch. Then, regarding their biodegradability rate, these bio-based and biodegradable bioplastic present considerable difference among them. In this sense, while PLA and PBS are only biodegradable under industrial composting or anaerobic digestion conditions, PHB and starch are rapidly biodegrade in the label environments within the time frame of the corresponding certificates. So in these environmental terms, PHB and starch show more considerable advantages. Well, regarding the market aspects, as you may know, the bioplastic industry is a young sector with a huge economic and ecological potential. As shown in the figure, the global market for bioplastic is predicted to grow continuously over the next year. However, if the current biopolymer market is compared to the global production, unfortunately, bioplastic still represent less than 1% of the plastic global production. So in any case, predictions are positive, and according to the latest market data, the global production is predicted to grow by passing the 2% mark for the first time in the following years. Within the biopolymer market, figures claim that biodegradable polymers double the market share compared to bio-based but no biodegradable polymers. And the trend is that this difference will continue growing. Moreover, addressing the different application of biopolymers, bioplastic are used in a wide range of markets, such as packaging, consumer electronics, automotive, toys, or textiles. More specifically, regarding the figures in the textile sector, around 22% of bio-based plastics are used for textile application, whereas only 3% of biodegradable plastic are used in this sector. So textile sector should make important efforts to increase the use of bio-based material, thus contributing the reduce of the current problem of the textile waste accumulation. Well, once we have analyzed the global market, in the following slides, I would like to comment the recent development made in ITES with the biopolymer that has shown the most promising properties for textile application, and also which is called to replace PET, that's it, PHB. So to this end, ITEX holds a wide range of plans aimed to cover the whole value chain. For example, for the first stage, the spinning process, ITEX has pilot plans for monofilaments and multifilament melt spinning, as well as texturizing pilot plans to confer desirable properties to the yarns, such as softness and comfort or bulkiness. In the second stage, once yarns are obtained, they are transformed into fabrics or textile products using weaving and knitting techniques or braiding also. Well, firstly, aiming at obtaining monofilaments for agrotextiles application, monofilaments with competitive mechanical properties were obtained. Namely, a monofilament with tenacity close to 3 grams per denier was obtained, which is very close to the values reached for PLA and their synthetic benchmark, PET, which shows 3.5 and 4 grams per denier respectively. Once the monofilaments were obtained, for one hand, a sound misses for agrotextile and packaging application were developed by weaving techniques. On the other hand, ropes with different thicknesses with application in the agriculture sector were obtained using the breeding machine. Addressing agrotextile application, we also obtained flat tapes using the monofilament melt spinning approach, and then in a second stage, we developed raffias using the weaving machine. So all these kind of agrotextile products have a huge potential to replace the synthetic benchmark thanks their competitive mechanical properties, and evidently, such as was previously commented, due to its biodegradability on all environments. On the other hand, in order to validate and foster the use of PHB for fashion industry, from the ropes and raffias obtained using monofilaments and flat tapes, we designed two handbags as prototypes, which validated the proper use of PHB for fashion application. Aiming at developing a specific yarn for clothing industry, multifilament composed of 96 filaments were obtained using the multifilament pilot plant. The mechanical properties for these multifilaments were not so competitive than the developed monofilaments. But anyway, we obtained jar with tenacities close to 1.8 gram per denier, while PLA and PET reached values close to 2.5 and 3, respectively. So in this field, we may keep working to develop jar with better mechanical properties. But in any case, in order to validate this yarn in the subsequent weaving and knitting processes, as well as to study possible problems during the process and the final aspect of the fabrics, we develop different twill and taffeta fabrics, obtaining items very similar to fullards. In order to develop more PHB prototypes for fashion industry from multifilament jars and using the flat knitted machine, we made a seamless jersey. So despite mechanical properties are not so high that we would like, fibers have enough tenacity to be knitted, thus validating the use of this biopolymer for this kind of application. For further research, in this case, we obtained a black multifilament using bio-based dyes in master batch form by compounding. And in this development, due to the presence of dyes, rheological properties were modified and the mechanical properties were slightly lower than the raw one. In any case, the validation of these black multifilaments was also done through the flat knitting machine to obtain another new black seamless jersey. Another example of validation of PHB resin for textile application was performed using the circular knitting machine. More specifically, from texturized multifilament yarns, we obtain socks with different density. And that's all from my side. Thank you very much for your attention. And if you have some question or any comment, don't hesitate to contact me.
Thank you, Aide. I was explaining that you have bring us different ideas, and we expect that also an inspiration for the participants. They can prepare a proposal and submit and these two Eurocluster projects. I would like to know what are the development of these biopolymers. It's they are in a TRL quite high to easily scale up and have the option to develop new products.
Yeah, for sure. I think we have to foster the companies to try to implement this technology. The technology exists because PET and PLA, the process is the same using multifilament, but we have to foster the companies in order to replace PET for this kind of biopolymers. The problem right now is the cost of the biopolymer, but talking with companies like Antex or Brillen, the PET price is being higher and the cost of biopolymers is decreasing. So maybe in the following years, they will be much. And also, I would like to highlight that there is a great advantages of this kind of biopolymer because the temperature to process is nearly 100 degrees lower, so the saving in the energy is really considerable.
Okay, thanks. We have a question in the chat. Pierre.
Hello, can you hear me?
Yes.
Yeah.
Yes, Pierre Lemeshko from IRMA in France. Thank you for the presentation. It was very interesting. And I'm curious about the PHA used for the monofilament and multifilament. Was it a homopolymer of PHB or a copolymers of PHB V or PHB and 4HB?
Our biopolymer is a copolymer between PHB and valerate, the valerate monomer. And we don't know exactly the composition because our supplier give us the resin and we study the spinning parameters, and then we give feedback to the supplier, and they modify the polymer in order to improve the processing parameters and improve the mechanical properties. So we are working shoulder to shoulder in order to improve this polymer and make it tailored to the textile application, because the degree or the composition for packaging is completely different for textile application. In fact, the composition is also different if you want to work with a monofilament pilot plant and if you want to work with a multifilament pilot plant. You should to make a different composition, a different that's all. I mean, a different using different additives, like in order to change the rheological properties or something like that, or maybe the elasticity is you have to make you have to make a engineering for a concrete application, a specific application.
Okay, thank you.
If you have any questions, you can raise your hand now, or if not, as we are on time, maybe we can share the last slides, and we can invite you also to.
For sure, I will send you the presentation, and you can share with the attendants.
Okay. Thank you, Ede. It was really interesting and also inspiring. We will wait for your presentation to share with all the participants, and we would like also to invite them to join us in the next webinars that we have organized in the frame of the digital transformation, and they will be organized by one of the partners of the xBUILD project. In this case, we will have the digital transformation on 26 April, then artificial intelligence for non-programmers and applicability for the three sectors of xBUILD EU as textile, construction, and advanced manufacturing on 10th May, and the last one on 24th May, data driving analysis and case studies. We hope you can join us and participate in these activities. Thank you very much for your attention, your participation, and we hope to see you in the next activities.